Today's aim is what are some of the basic geometry theorems and postulates. So these are theorems and postulates you're going to need to know in order to do two-column proofs. Now the theorems, many of them you already know. Some of the postulates are not as obvious. So we're going to go through some of them, and even if you already know it, please watch the video and that will reinforce what you already know. So the first thing is, let's define what a postulate is. And if you remember, a postulate is a statement whose truth is accepted without proof. In other words, we just accept the fact that this statement is true. It does not need to be proven. As opposed to a theorem. So a theorem is a statement that is proved by deductive reasoning. This, of course, should already be in your theorems and definitions, so this is just review for you. Let's take a look at something that might not be obvious to you, and this is a postulate that basically says the reflexive property of equality, or just plain the reflexive property. What does the reflexive property mean? It means a quantity is equal to itself. It can be applied to a line segment or a side of a triangle, or it can be applied to an angle. Okay, so you can apply it to the side of two triangles, or you can apply it to an angle that is shared by two triangles. Let's take an example. How is it going to be applied to a side? So imagine I wanted to prove that triangle ABD, this left triangle, which I'll call triangle 1, is congruent to triangle 2, triangle CBD. Remember, the only thing we can use are the triangle congruence postulates or theorems to show that they are equal. But one of the properties I can use is the fact that both of these triangles share what? They share this line segment BD. It is a line segment that is shared by both triangles. So you'll notice that in triangle ABD, in this triangle right over here, triangle ABD uses line segment BD, and you'll also notice that triangle CBD, this triangle right over here, CBD, uses that same line segment, that same side, BD. So you'll notice that both of these triangles use that same line segment, BD. So in my proof, how would I use this? What I would say in my proof as one of the statements is that line segment BD is congruent to line segment BD. And the reason would be, as you guessed it, the reflexive property. Similarly, I can use the reflexive property when I'm talking about angles. Now, in this case, we have overlapping triangles in the case of the figure on the right. And it might not be as obvious to you, but let's take a look at the two triangles I'm talking about. So first triangle is going to be triangle ABE, or triangle ABE. And the other triangle that we're talking about is triangle CBD, triangle CBD. And I try to use different colors to show you the distinction between these triangles. So one is the purple triangle, triangle CBD, and the other one is triangle ABE. Notice how they both use, I know this is poorly drawn, they both use angle B. Angle B is shared by both triangles. It's the same angle B. Angle B does not change sizes just because I'm changing the triangle. So one of the statements in my proof would be that angle ABE is congruent to angle ABE is congruent to angle CBD, angle CBD. Notice, if you will, that B is in the middle in both of these triangles. So B is being shared by both triangles. So I would say angle ABE, that's supposed to be an E, angle ABE is congruent to angle CBD, and the reason, of course, would be, as you guessed it, the reflexive property. So here you have a reflexive property used for line segments, and here you have an example of the reflexive property being used for angles. Okay, let's take a look at another property that we're going to talk about. Okay, and it's actually a postulate, and you can use postulate and property interchangeably. It's perfectly fine. So one is called the substitution postulate, and substitution postulate basically says that a quantity may be substituted for its equal in any statement of equality. What do all these words mean? Well, they mean that, look, if angle 1 is equal to angle 2 and angle 1 is also equal to angle 3, what do we know? Well, let's see. If angle 1 is equal to angle 2 and angle 1 is equal to angle 3, then clearly that would mean that what? Angle 2 is equal or congruent to angle 3. What allows me to say that? Well, look, Angle 1 and angle 2 are congruent to each other. They have the same size and the same shape. Angle 1 and angle 3 are congruent to each other. They have the same size and the same shape. So what I'm doing essentially is I'm taking this statement right over here, and I am taking this angle 1 and I'm substituting it with angle 2. Remember, whatever angle 1 is, so is angle 2. So if angle 1 is equal to angle 3 and angle 1 is also equal to angle 2, then I can say that angle 2 is equal to or congruent to angle 3. Why? Because what have I done? I have substituted. So my reason for this statement is the substitution postulate. This should also be written in the theorems and definitions section of your binder. You are going to need it. If you need to put your player on pause, go right ahead and hit play to resume. Okay, the next postulate you need to know is very similar to the substitution postulate, and it is called the transitive property. Now, you'll notice that I'm using the same angles, 1, 2, and 3, but the order in which I'm using it is slightly different. So for example, here in the second case, what I'm saying is angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3. Well, what does that mean? That means that angle 1 is congruent to angle 3. It's very similar to substitution, but what we're saying is 1 is equal to 2 and 2 is equal to 3. Therefore 1 and 3 must be congruent to each other. Okay, so for example, if this was 30 degrees, right, and angle 2 is also 30 degrees, because after all they are congruent to each other. And if angle 2, which is 30 degrees, is congruent to angle 3, which is also 30 degrees, then it must be true that angle 1 and angle 3 are congruent. And sure enough, they are. Angle 1 is 30 degrees and angle 3 is 30 degrees. So how do we draw a distinction between substitution postulate and the transitive property? Well, this is how I like to think of it. Transitive sounds like train, train. So imagine you have 3 cars, right? The red car is pulling the orange car, and the orange car is pulling the yellow car. Therefore, indirectly, the red car is pulling the yellow car. So in other words, we have this chain. We have this chain in our link between the red car and the yellow car. The red is pulling the red is pulling the orange is pulling the yellow. Therefore, indirectly, the red is pulling the yellow as well. Angle 1 is congruent to angle 2. Angle 2 is congruent to angle 3. Therefore, angle 1 is congruent to angle 3. And of course, you can add as many chains as you want. If you wanted to say angle 1 is equal to angle 2, and angle 2 is equal to angle 3, and angle 3 is equal to angle 4, etc., then we can say angle 1 is equal to angle 4 by the transitive property. So that's the second property you need to know. So these belong in your notes. If you need to put your player on pause, go right ahead and hit play to resume. Okay, so let's see how we can use the substitution property in a formal proof. So it says, given BD is the angle bisector of ABC and ABD is congruent to angle 1, prove that DBC is congruent to angle 1. So the first thing I want to draw your attention to is how we approach a proof. And if you remember, one of the things we said is there are certain steps we need to take. Number 1, mark up your diagram in pencil using the information given. So let's mark this up. It says BD is the angle bisector of ABC. BD is bisecting angle ABC. Well, what do we know because of that? Well, if BD is an angle bisector, that means BD cuts angle ABC in half. So I'm going to put these little arcs right over here. Here's one, and here's the other. All I'm trying to do is to show that angle ABD and angle CBD are congruent to each other. Now, what else are they telling us? They're saying that angle ABD is equal to angle 1. ABD, which is this angle right over here, is equal to angle 1, which is this angle over here. So what they're asking us to prove is that angle DBC, namely this angle, the red arced angle, is equal to angle 1. Well, you can see where we're going with this. So let's actually set up our proof. And the first thing we're going to do, of course, is we're going to talk about what we're planning on doing. ABD and CBD are congruent, because that's the definition of an angle bisector. An angle bisector bisects an angle. It cuts the angle in half. And if they're telling us that angle ABD is equal to angle 1, if this angle over here, ABD, is equal to angle 1, and angle DBC is equal to angle ABD, well, that means that angle DBC must also equal angle 1 by the substitution property. Let's actually write this down as a formal proof. So here's my T, and on the left side go my statements, and on the right side I have my reason. Okay, So my first statement is going to be that BD is an angled bisector of ABC. So my statement number one is going to be that line segment BD, right, is the angle bisector, is the angle bisector of angle ABC, angle ABC. And the reason for that is, well, as you guessed it, it is given, right? So I write given. Everything that is given has to be written down. Well, what do I know because of that? I don't want to immediately write down ABD is congruent to angle 1. I want to jump off this statement saying that BD is angle bisector of ABC. That would mean that ABD, angle ABD, and angle CBD are congruent. So let me say that now. Let me say now that angle ABD is congruent to angle CBD. And the reason for that would be an angle bisector divides an angle into two congruent angles. Or I can just say definition of angle bisector, right? What is an angle bisector? An angle bisector is a line segment that divides an angle into two congruent angles. So that is my reason for saying that angle ABD and CBD are congruent. Okay, lovely. So now what do I have? Well, now let me take down what they're giving me. The fact that angle ABD is congruent to angle 1. Angle ABD is congruent to angle 1. And what's the reason for that? Well, it is given to us, right? So I'm going to say given. Well, let's see what we got here. So far we have BD being an angle bisector, which means that angle ABD and CBD are congruent. But we also have been told that angle ABD is congruent to angle 1. Well, let's see what we got. ABD is congruent to CBD. ABD is also congruent to angle 1. Well, my fourth and final statement has got to be what? That angle CBD, sorry, angle DBC, they call it DBC, CBD, DBC, it makes no difference. Angle DBC is congruent to angle 1. That's exactly what I was being asked to prove. Angle DBC is congruent to angle 1. And what have I done? Well, I've substituted. Wherever I see ABD, I'm substituting that with angle 1. Because remember, ABD and angle 1 are the same. So wherever I see ABD in this statement, I'm substituting that with angle 1. Here's angle CBD or DBC. These are exactly the same thing, right? CBD and DBC are exactly the same thing. These things are exactly the same thing. And all I'm doing is I'm substituting angle 1 for ABD. So the reason for this is going to be substitution. Okay, and we're done. What I'd like you to do is make sure you have this proof in your notes. What I'm going to do is I'm going to flash the version that looks much better than what I've written. Please put your player on pause. Make sure you've got the diagram and the statements and reasons down before you hit play to resume. Okay, so let's take a look at another postulate that you need to know, and that is called the partition postulate. And the partition postulate is actually something you already know because it's logical that the whole is equal to the sum of its parts. So let's take an example. I have line segment ABC here, ABC. AC, this big line AC, is equal to two pieces, AB plus BC. In other words, I'm adding AB and BC together to get big line segment AC. It is that simple. The whole is equal to the sum of its parts. You can say an iPhone is equal to the sum of its parts, its screen, its internals, its memory chip, etc. So here we're saying that the whole, in this case the whole line segment, is equal to the sum of its parts. What are its parts? Well, AB and BC. We're not saying anything about the length of AB and the length of BC. All we're saying is that if you add AB and BC together, you get AC. That's all we are saying. Okay, so let's take a look at another postulate, and that is called the addition postulate. Again, folks, this belongs in your theorems and definitions. Put your player on pause, make sure you got it down before you hit play to resume. Okay, the addition postulate, which also belongs in your theorems and definitions. It says as follows. If equal quantities are added to equal quantities, their sums are equal. Now this may seem really confusing because the word equal is used twice, and we have added, we have sum, we have we have quantities that's used twice. So what are we trying to say? It's very simple. If A is equal to B and C is equal to D, then A plus C is equal to B plus D. Let's take examples. Suppose A was 5. That means B must also be 5, because if A is equal to B and A is 5, then B is equal to 5. And C is equal to D. Let's take a value for C. Suppose C is 2. Right? Well, if C is 2 and C is equal to D, that means D must also be 2. Well, that means that A plus C, which are these two guys here, A plus C, which is basically 5 plus 2, is equal to B plus D, which are these two guys. And this is also 5 plus 2. And it's true, 7 is equal to 7. So when is this used? Let's take an example. I have line ABC, and I have line DEF, ABC, DEF, with AB equal to DE, and we have these two hash marks showing that AB and DE are congruent, and BC equal to or congruent to EF. BC is the same size and shape as EF. So what we're saying is that the addition postulate says that if this is true, that AB is equal to DE and BC is equal to EF, that means that AB plus BC is congruent to DE plus EF, which is exactly the same thing as we have here. If A is equal to B, let's say they're both 5, and C is equal to D, let's say they're both 2, then A plus C, 5 plus 2, is equal to B plus D, 5 plus 2. So AB plus BC must be equal to DE plus EF by the addition postulate. Similarly, I can say the same thing for angles. I can apply the same addition postulate for angles. ABD is equal to EFH. ABD, which is this angle right over here, is equal to EFH, this angle over here. What else are they telling me? They're also saying that DBC, which is this angle over here, which I will mark in yellow, I hope it's easy to see, is equal to HFG. Well, what does that mean? If that's the case, then that means that angle ABD plus DBC, angle ABD plus angle DBC, is congruent to which two angles summed together? Angles EFH plus angle HFG. For what reason? Because of the addition postulate, exactly the same postulate. This belongs in your theorems and definitions, so you should take this down. Now, put your player on pause, and then you can hit play to resume. Okay, so let's apply the addition postulate to an actual proof. So I'm going to keep the postulate up here. It says if equal quantities are added to equal quantities, the sums are equal. If A is equal to B and C is equal to D, then A plus C is equal to B plus D. So here's the proof. Given ABC and DEF with AB congruent to DE and BC congruent to EF. So how would I prove that AC is equal to DF? Well, if you remember, I just showed you how to do that. The first thing we're going to do is let's use the partition postulate. What did the partition postulate say? It said the whole is equal to the sum of its parts. So what I'm trying to show eventually to prove is that AC, this big line segment AC, and DF are congruent to each other. So first what I want to say is that AC, this big line segment, AC, this big guy right here, AC, let's use another pen, AC is made up of two things. It's made up of AB plus BC. So let me write that. In other words, AC, line segment AC, is equal to, or is made up of what? Of line segments AB plus line segment BC. And I also know that, I'm going to say it in the same sentence, in the same statement, that line segment DF, right, this big line segment here, line segment DF, is made up of what two line segments? Well, it's made up of line segment DE plus line segment EF. And the reason for that is, as you guessed it, the partition postulate. The whole is equal to the sum of its parts. Now, what's the next statement I'm going to say? Well, look at what they're giving me. They're telling me that AB is equal to DE. See, AB is equal to DE, the two hash marks. So my statement number 2 is going to say that AB is congruent to line segment DE. Okay, and I'm also going to say that line segment BC is congruent to EF. You can see that by the single hash marks. So let me also say that line segment BC is congruent to line segment EF. And the reason for that is, well, it's given. That's the reason. Okay, so what do I want to do? I want to say that AB plus BC is equal to DE plus EF, right? And the reason for that is, as you guessed it, the addition postulate. Okay, so statement number 3 is going to be that AB plus BC, remember, AB is equal to DE, BC is equal to EF. So AB plus BC, so I have AB plus line segment BC is equal to, that's supposed to be a C, AB plus BC is equal to line segment DE plus EF. And the reason for that is the addition postulate, right? The reason for this is the addition postulate. Now I just gave away my final statement. This is the addition postulate. So if that's the case, let's take a look at what's happening. AB plus BC is equal to DE plus EF, right? AB plus BC is equal to DE plus EF. But one second, AB plus BC is AC. AB plus BC, this guy right over here, which I will underline in red, AB plus BC is this same AB plus BC. And DE plus EF is the same thing as this DE plus EF. Well, what does that make these two, AC and DF? What are they to each other? Because that's what I'm being asked to prove. Prove that AC is equal to DF. Well, if AC is equal to AB plus BC, and AB plus BC is equal to DE plus EF, and DE plus EF is equal to DF, well, that would make AC and DF congruent because of the substitution property. What I'd like you to do is, here it is rewritten slightly more neatly, actually much more neatly. Please make sure this is in your theorems and definitions. It needs to be in your theorems and definitions. It is a proof. You're going to use this. So make sure it is down in your notes. Put your player on pause and hit play to resume. Once you have all the steps down, it is written neatly and nicely for you. You don't need to say the whole is equal to the sum of its parts. You can just say the partition postulate. This is there just to remind you of what the partition postulate is. Okay. Let's take a look at the application of the addition postulate and the partition postulate, not with line segments, but with angles. So here we go. So it says given ABD is congruent to EFH. So one more time, we are going to draw these nice arcs here. So ABD is congruent to angle EFH, and it's saying that DBC is congruent to angle HFG. In other words, these two angles are congruent to each other. Maybe I shouldn't be using yellow. Maybe yellow is a little too bright. We're saying that these two angles are equal to each other. So once again, what do I want to show? They're asking me to prove that ABC, big angle ABC, is congruent to angle EFG. So again, I'm going to start first by using the partition postulate. I want to say that ABC, this big angle ABC, is made up of what? It's made up of ABD and DBC. So my first statement is going to be that angle ABC, is congruent to angles what? Angles DBC, this guy right over there, right? Angle DBC plus angle what? Plus angle, angle ABD plus angle DBC. It makes no difference which one you write first, but let's, for the sake of argument, let's just write the first one. Let's just write ABD as the first angle. So ABC is made up of angle ABD, plus angle DBC, angle DBC. And while we're at it, let's also say that angle EFG is congruent to what? It's congruent to the sum of which two angles? Well, it's congruent to the sum of angle EFH and angle HFG. So I say it's congruent to angle EFH plus angle HFG. And the reason for that, of course, is going to be the whole is equal to the sum of its parts, or just plain the partition postulate. And I misspelled it. So let's do this again. It is the partition, and partition POST dot is perfectly fine. The whole ABC is made up of the sum of its parts. The parts are ABD and DBC. What is the second statement I'm going to make? Well, first of all, let me get these givens down now. Notice how I'm not always starting off with the givens. I want to start off with something I already know, and then I'm going to use the givens in my favor. So the given is that angle ABD is congruent to angle EFH, that is given to me, and also that angle DBC, is congruent to angle HFG, right? HFG, and I mark those with those two hash marks. And the reason for that is, as you guessed it, it is given. That is given. Well, what is statement number 3 going to say? Well, remember, what I want to show is that if I add ABD plus DBC, I get ABC, right? So I want to show that ABD plus DBC is equal to EFH plus HFG, right? So in other words, what I want to show is that ABD plus DBC, if I sum these two angles, they equal to the sum of these two angles, right? So what I want to do is I want to show that ABD plus DBC, angle ABD plus angle DBC, is congruent to what? Is congruent to angle EFH plus HFG, angle EFH plus angle HFG. So ABD plus DBC is equal to EFH plus HFG. Okay, and the reason for that is the addition postulate. The addition postulate. Okay, so what is my fourth statement going to be? Well, let's see. So I said that ABC is congruent to ABD plus DBC. The whole is equal to the sum of its parts. Same thing here. EFG is equal to EFH plus HFG. Now remember, ABD and EFH, ABD, which is this angle over here, and EFH, which is this angle over here, they are equal to each other. And DBC, which is, let me do this in a different marker, this angle over here is equal to or congruent to this angle over here. That means if I sum these two angles, they are equal to the sum of these two angles, which allowed me to say statement number 3, ABD plus DBC is equal to EFH plus HFG. But let's not forget that what is ABD plus DBC equal to? ABD plus DBC is equal to ABC, right? Is equal to ABC. And what is EFH plus HFG? EFH plus HFG, that is equal to EFG, right? Well, wasn't that exactly what I was asked to prove? In other words, I was asked to prove that ABC and EFG were identical, were congruent, and that's exactly what I'm going to say right now. In other words, I know now that angle ABC is congruent to angle EFG. What allows me to say that? Well, remember, what I'm going to do is I'm going to take this statement and I'm simply going to substitute it with ABC. And that's what this is all about. What am I going to do with this statement over here? The part of this statement here, EFH plus HFG. EFH plus HFG is equal to EFG. So that's what allows me to substitute EFG for EFH plus HFG. So the reason for this is going to be the substitution postulate. Or you can say the substitution property. Postulate or property is perfectly fine. Please make sure this is down in your notes, and I'll write it much more neatly for you right over here. So put your player on pause if you need to, take down the diagram, take down the given, the proof, the statements, and the reasons. And it might be that you need to actually read this a few times until you absolutely get it.